I'm going to describe how to use an interactive simulation that models CSTRs in series and their resonance time distribution. The simulation is on the LearnChemE site at this link. And the idea is we have the CSTR where we have a feed in the first CSTR, and the exit from the first CSTR is a feed into the second, the exit from the second feeds the third, etc., up to total in CSTRs. We might use several CSTRs in series, 3, 4, even 5, to obtain desired properties in a reaction, a certain selectivity, for example. Or we might also use a lot of CSTRs to model a plug flow reactor. And so the simulation looks like this, where we can change the space-time, and this is the space-time for the total system, not the space-time for one CSTR, but the space-time for n CSTRs. And then 12 is the number of CSTRs in series. So this resonance time distribution, probability of a molecule leaving at a certain time. So the total probability area should end up being 1. And the behavior is, if you notice, it's centered. The maximum is not at 60. It's actually less than 60. It's not a symmetrical distribution. And let's look at what the simulations look like for different numbers of CSTR. So let's go to the simulation. So in the simulation, the details show the equations we use to obtain this resonance time distribution. The idea, one way to obtain it is imagine injecting a pulse into the first CSTR and then watching the concentration of that tracer at the outlet of the 5th CSTR, the 10th CSTR. That's what essentially you're looking at, and the resonance time distribution is just a normalized version of that outlet tracer concentration. So if I change the space-time for one CSTR, notice that the highest probability of molecules leaving the CSTR is at time 0. Because if we inject a tracer, it's evenly distributed throughout that CSTR instantaneously if it's an ideal CSTR. And that means we have the highest concentration of the tracer at time 0. And since the exit concentration is equal to the concentration of CSTR, we have the highest exit concentration at time 0. So for one CSTR, we have this exponential decay. But now we go to 3 CSTRs, there's 0 concentration of that tracer at time 0, because at time 0 nothing has yet gotten to the second CSTR, much less the third CSTR. But it's an asymmetric distribution. Here the space-time is 45, but the maximum is lower. And now as we keep increasing the number of CSTRs, then what's happening is resonance time distribution maximum is close to the space-time. And then if we change the space-time, the curve, of course, changes. So the idea, number of CSTRs in series, certain advantages for obtaining desired reaction rates. Volume of 3 CSTRs is going to be less than 1 CSTR, for example, to obtain the same conversion. But there are certainly other advantages to multiple CSTRs. And we can measure this to determine how well a system behaves like 25 CSTRs in series by using tracer injection and detection at the outlet.